Good afternoon. You have a form in front of your waiver, okay, we're going to go on Monday, and we should be pretty good on our timing. We have classes after this, is that right? Everybody has a class after this? Okay, so what we should do then is, I'd like to meet, can we meet a half an hour earlier than normal? In other words, can we meet at, say, roughly 10 minutes to 1? Is that acceptable? All right. There's a bus, so we will all go together, and that's a liability issue, so we have to do that. You can't just decide, well, I'm not going to go with the bus, I'll go with the car. Okay. So the university will require you to go. We go all as a group, basically. It's not a long drive. Okay. It's literally across the street from the Alpha Station post office. Okay. We are currently in the village of Alfred, the town of Alfred Station. We are within that. Okay. So right down here is like, I'd say conservatively 3 minutes away. I'm driving probably 2.5. Right? This sheet, I want you to sign up if you're here. Everybody has the permission form, right? So you can sign that. Just make sure that I get that back before you leave. The sign up on here, this does two things. One, it lets me figure out who's not here, so that I can reach out, make sure that they're able to go on Monday. Second thing it does is, what's that? Can we do on those? Is your name on there? Yeah. Okay, sign your name next to that. Okay. So, all right. So, and then pass it on. The registrar wants to know if you're here. That's the other part. Usually I just ignore that, but he's a new registrar. I'll try to get him a good sign to begin with. That'll be temporary, but at least get him a good start. Okay. So, questions? Yes.
So you already have a hard hat
You have your own hard hat? Yeah, bring it. We have 30, I believe, which is exactly the number that we need. So yeah, if you have a hard hat, bring it, because you know things happen. Like somebody borrows a hard hat and then you shy one. Yes, bring your own hard hat if you have it. Other questions?
I was having a little bit of trouble with question 9D on homework. It's about expected diametral shrinkage during the intermediate to get the final density and not the theoretical density. Are we assuming the initial density from part A?
Yes. Okay. And there's another assumption. What's your assumption? Does it say, normally my questions say, state any assumptions.
Right.
It's a good idea to do that. What's my assumption? What's your assumption?
My assumption is that velocity after synchrony would be 0, matching theoretical density.
Okay, so that's actually not an assumption, that's defined.
Okay.
What's your assumption? There is an underlying assumption in the question. Yes?
I would say that you have to assume that there's nothing in the place before.
No.
No?
No, I mean, they're pore spaces. I mean, by definition, they're empty.
But I mean, like, there's no water.
Well, it does say that it's been dry, right? After drying. One assumption, and that is that your sample is behaving isotropically, it's going to shrink in an isotropic manner. That means it shrinks the same way in all directions. Good. We recently got involved in a situation that's quite odd, and that is that there is anisotropy associated with dry pressing in a direction that there should not be. Okay, so normally what you assume is that in your compaction direction, you would likely have more shrinkage than you do in your XY direction, but in this case, you have more shrinkage in your XY direction than you do in your compaction direction. This is an odd result, but that's your underlying assumption is that this is isotropic. That means that it's a sphere when you start and a sphere when you end. Good? It's not critical to answering the question, it's implied, but I think that we make a lot of assumptions in stuff that we do. You should start thinking about what those assumptions are, whether they have an impact on what's going on. Good? All right. Any other questions? So I have to get the homework assignment posted, right? So, okay. Let's see. We're about to launch into product characterization, but I think we have a little bit more to do on raw materials. This is where we left off. It's on froth flotation. Can someone tell me in a single sentence what the benefit of froth flotation is?
This is separation of hydrophobic and hydrophobic.
Now, what's the benefit? It's cheap. Not necessarily.
Safe as an methods.
Nah.
It's
We don't care about safety.
surface chemistry driven, so we can
No.
filter it.
Once you filter out what you don't want or what you want.
Is that ORE? What's the benefit of froth flotation? Allows us to beneficiate deposits that do not have a lot of the material that we want, right? I mean, that's the issue, right? So you're bringing in a process that's not necessarily cheap, but allows us to process ores that we would not be able to process if it was not for froth flotation. Good? Because you're able to then, if we take this copper deposit, which was in Montana, which was absolutely immense, right? The Berkeley pit, which is in, is it Bozeman, Montana? Is that it, right? Anyway, Berkeley pit is the largest EPA Superfund cleanup site in the world. Right? Reason for that is that the copper sulfide often comes with arsenic. It is a mineral that gets deposited at the same time, and the consequence of that is that whole area is just contaminated with arsenic, basically. So that means, interestingly enough, nothing grows in that area, and that's actually true. You should go to the Berkeley pit. You should look it up. It's absolutely huge. It's a strip mining operation, and they took out millions of tons of copper out of this hole in the ground at 6% copper sulfide in the ore. So you're talking about huge amounts of material that can be processed relatively efficiently. There's no other way to do that. And so froth flotation allowed them to beneficiate that ore and then extract from that copper metal, okay, which was immensely important at the time. Okay? Then. All right. So, that's the benefit of froth flotation. We have these schematic ideas. I don't need you to know a lot about this. I don't care if you can remember what a collector or a frother is. All I want you to know is that this is a remarkably useful technique. I won't say it's necessarily efficient, but compared to other methods, it's efficient for being able to separate out small amounts of material. So there's a lot of work has been done, a lot of work, typically in chemical engineering, to understand the stability of the foam. Okay. So the idea is you're going to create a foam that has sufficient strength and stability to lift these particles out of that system and separate them. And if your foams break down, then your particles go back into suspension, and then you're not getting what you want. So there's a lot of work been done on that, a lot of theory on foam generation. I don't care about any of that. I want you to understand that froth flotation is a really effective means of separating or beneficiating ore deposits which have low concentrations of material. And they come up with different ways of doing this. They're looking at how do you basically remove material. And I'm not going to spend much time with that other than showing you cartoons of how it works, basically. Okay, so this is used in a lot of different ore processing facilities. Okay, particle sizing. We're going to talk quite a bit about particle size distribution coming up. And we're actually doing some research in that area, which is interesting, because I don't think anybody's worked in particle size distributions for a long time. You may think that it is mundane and uninteresting, but you would be incorrect. Okay? And so sieving is the most common and the simplest method. It is efficient, okay? You can separate by sieving huge volumes of material effectively and efficiently. And that's where vibratory separation comes in. So vibratory screens, essentially material comes in and the screens vibrate. Material that gets caught on the screen gets moved over and gets pulled off. Material keeps coming through. It's a continuous process. So you can sieve immense amounts of material. We go to the gravel pit on Monday. They have a very, very simple setup for eliminating huge boulders. It's simply a series of steel rods, and the rocks come in basically, something looks really like that, typically inclined, okay, like this, and the material gets dumped in, and the rocks come off, and the finer material goes through. It's a very simple setup, very efficient, okay? And so you can separate out the boulders. They separate out the boulders because the processing facility can't handle rocks above a certain size in the jaw crusher. Okay, and I mentioned the jaw crusher is breaking this material down, and if you get a big rock in there and it blocks the jaws open, a bunch of other stuff falls through and doesn't get crushed, right? So they separate that out first, and then whatever's left can range from the size of a grain of clay, if you will, up to anything that will fall through that opening. Okay, and that's set up. What happens in that material, in the sieve, if you will, sieve is just a more sophisticated means of this, where instead of being, of course, one direction, we have essentially a square, and the idea is based on a small particle or a spherical particle of a certain size will fall through that opening. This is what we get out of that gravel deposit ranges from something that's roughly the size of a clay particle, potentially submicron, up to things which are centimeters in diameter. Okay, and so potentially huge, but it's a gravel deposit, right? So you don't typically get huge out of a gravel deposit. That's not necessarily true, but your percentage is small. If you drive by the gravel deposit, they have these huge stones that came out of the gravel deposit, right? And so, do you care about those? Not really. Most of it's in this size range, which is of the order of a few centimeters down to microns, and they get separated out, and then that's the first pass. Vibratory screening is really common, and they do that as well. Hydrocyclones are different. We're going to get to those in a minute. Okay, so when we start grading particle size distributions, and we're going to talk about this a little more. This is just an example for coal dust, and they separate by size. We separate by size. All the particles look to be the same size. But I want you to recognize in this image, you have big particles, you have really small particles, and that's actually the indication of what we will call a log normal distribution, which we're going to talk about quite a bit more. Hydrocyclone is a different animal. It's actually a really efficient means of removing small particles from larger particles in suspension. Hydrocyclone can be used in ore beneficiation processes. It's used in clay processing. Although most of the clay that's mined in the United States is used for, what is most of the clay mined in the United States used for? I'll give you a hint. It's not ceramics. Well, that's not much of a hint.
Concrete.
What's that?
Isn't it used for concrete?
No, nobody uses clay for concrete that I'm aware of. Maybe a little bit of clay to go in and make calcium aluminates, but where's clay go? What's the biggest use of clay? Pottery. That would be ceramic. Is that confusing? Oh, you're biomaterials, I forget. Yeah, that's confusing. Ceramic and pottery. My tachometer is firmly off for the rest of the day. Good? Anyone else want to try? At that point, right? Used to coat paper. What? I could see Time magazine, it's not printed anymore. Paper that takes ink, bright colored papers are usually coated with clay. Okay, calcined clay takes ink better quality color, better resolution, higher quality. Okay, so 95% of the clays mined in the United States go to clay, go to do coat paper. Okay?
So you're
Yeah.
talking about like magazines? with
Yes,
the
like
different
right.
textures?
Say again.
With the different textures?
Yeah, the slick paper, right? That's where clay is used.
I have no idea.
Yeah, most people don't. It's not a lot, right? The paper comes out, and they make a slurry of, and they calcine the clay first, so it's a calcined clay product. And the paper comes out, it's on a slurry, and it goes under a doctor blade, and it's run at something like 2,000 feet a minute. And they're coating this paper, and it gets dried and put up on reels, and then it goes off to be printed. Okay, that's the #1 use of clay in the United States. And so, and probably in other places in the world as well. And then, depending on the calcination temperatures, depending on the impurities in the clay, dictates the whiteness of the paper, right? And the quality of the paper, and also then the cost. Okay. Now, the reason I tell you that is that hydrocycloning is used because what you end up in clay deposits is you end up with other particles that you do not want. Okay, and those particles are usually quartz or silica, but they're big. Okay, so clay particles on the order of maybe at most 2 microns across and about 1/10 of a micron thick. So they are plate-like particles. And they have this morphology, more or less. And this dimension versus this thickness dimension. Okay, this is thickness versus width, if you will. W divided by T is approximately 10. Okay, so it's a little thin platelet of material. And T is typically around 0.1 microns, so 100 nanometers thickness. Quartz particles tend to be between 30 and 100 microns. Okay, so you can take all these clay particles and you have a paper going under a doctor blade with a slurry on it, okay, and the clay particles are aligning under that doctor blade to provide that coating on the clay. And you get a quartz particle in here like this, and within 2 minutes, if you think about it in terms of the math, you get a quartz particle lodged in the doctor blade. Within 2 minutes, you've made a mile of bad paper. Okay, for a coating process, maybe say 3 minutes if you want, but 2.5 minutes. So you're 1,000 feet per minute type of thing, right? A short period of time, you made a lot of bad paper. So they don't want the quartz. So they take the quartz out, and they do it through hydrocycloning. So hydrocyclone looks something like this. It's typically a cone-shaped device, and there's a tube that comes down the middle, and it comes off. So the material comes around like this, okay, a spiral, and you have what's called the underflow, which goes out the bottom, and the overflow, which comes out the top, okay? And what you have is that this centrifugal force of the material moving around in a circle takes the particles and pushes them to the outside based on size. Good? So if you have with this force pushing the particles out, the coarse particles go to the outside, they come out the underflow at the bottom. The fine particles stay in the suspension, they go out through the middle of the top. So you can separate particles very effectively. You have a practical limit of your cutoff for size, which is around 5 microns, which is fine for our clay particles. In quartz particles that are 5 microns, we don't care about, right? But you're going to separate out the big quartz particles by hydrocycloning, and then you end up with your clay particles remaining in suspension, which is perfect. Okay. I was in Georgia at a clay facility, and they had a setup like this, where they had a whole series of hydrocyclones set up, and they're pumping fluid in there under pressure, and they're separating huge amounts of material. So they can be gang, as it says, as it implies here. So your inlet, and then the size of the cyclone dictates your separation limits. So the cyclones are sized based on what you're trying to do. So this is more or less the example of how it works. Material comes through, okay, and it's spiraling around, and then the material in the middle gets pulled out the top, the material in the bottom goes out, okay, and it's conical, it's cone in shape. And let's skip this because I want this slide. And what you have is you can, based on the velocity, you have a zero velocity line, and then what you can do is you can grade based on velocity how those particles move away. What you have is a separation in the middle that you can separate You can take the submicron particles off, for example, by where you take that center pipe and separate out the material. Okay? So, works very well, works extremely well for particles that are similar in density. Okay? It can work for particles of different density, but the problem is this, right? So we will get to this in a little bit. I think I can write it out. Let's see. 18 eta velocity divided by delta rho times gravity. This is equal to d squared. So this is Stokes sedimentation. Okay, so Stokes figured out that that particles will settle, right, based on the size of the particle squared. Density here, delta rho, is equal to the density of the particle minus the density of the fluid. Okay, so you can do this in air, for example, which we do. I had a great example, but I can't find it right now. Mount St. Helens erupted, I'm going to say 1980, I think it was. So it was a while ago. I suspect none of you were here then. But I remember I was in high school and it was awesome. When was the last time a volcano erupted in the continental United States? Not a trick question. You have to go look. It's been a while. If your answer should be 1980. Okay, so Mount St. Helens erupted, and it did something really cool. So what it did was it ejected huge amounts of ash into the atmosphere, right? And you have essentially a massive air classifier. And the really small particles went 200 miles, 1,000 miles away. The boulders went next door, you know, and as you moved across eastern Washington, you've got different sized particles based on the distance from the mountain. Is that screaming cool? Yes. Of course, there's a great picture. You go look up, what's the name of it? I can't remember. A friend of mine grew up there. It's a farming town in eastern Washington. And they're plowing ash off the streets like we plow snow off of the roads in the winter. So it was awesome. Okay. But the distance from the mountain, so the particles went in the atmosphere and then they fell back down. And the big particles fell first, in the shortest distance. So they had this little thing that you used to be able to buy in a trinket in a gift shop. And it had the ash collected from different distances from the mountain. So, awesome. So, Stokes, though, same thing in water. Okay, V is the velocity which the particle falls. This is gravity. Okay, this is viscosity. So what you have is you have a particle, right, is settling, and you get flow lines around that particle that create drag that slow that particle from settling. Okay, the larger the particle, the faster it settles. The higher the density of the particle compared to the fluid medium, the faster it settles. Okay, there's an underlying assumption. What is that assumption? Assumption? The particle is spherical. Okay, you should make a note of this. All particle size characterization techniques start with the assumption that the particle is spherical. Okay? The consequence of that should be that all particle size distribution plots should say on the x-axis, which is typically particle size, should say equivalent spherical diameter. But they frequently just say particle size. I do the same thing. But that's the underlying assumption. Stokes assumed that the particle was spherical. Okay? And then this term is velocity. So if you wanted, you could rewrite this equation and say the time required for a particle to settle as given distance, right? So velocity is then x divided by t, okay? It's going to be 18 times viscosity times your distance divided by delta rho, difference in density, gravity times b squared. So what you see is that when d gets bigger, time decreases. Your velocity or your difference in density gets larger, okay, then your time decreases. Right? Gravity, why would I worry about gravity?
I want to say if you want to try this on another planet.
Yeah, we could go to other planets to separate particles, not particularly practically. Right? Used to say of all the planets, I like this one the best. All right, so none of you are paying attention at all, are you? So, but you can use a centrifuge, right, to mimic an increase in density, so you can actually cause the particle to move faster because you can increase gravity by using a centrifuge. Viscosity increases, your time increases. Your distance increases, your time increases. Okay? So a particle settles in that condition, right? Now, when I said that we would like that hydrocycling works great for particles of the same density. So if I'm removing quartz from clay, perfect. Because quartz and clay have just about exactly the same density. But if I have a particle of a higher density, okay, then it will settle at the same rate. A smaller particle with a higher density can settle at the same rate as a larger particle of a lower density. Make sense? Okay? So now I have a problem with hydrocycling. So there was a project done years ago to separate, maybe I got the equation right, to separate particles that were pigments used in industrial process, and they all went into the same waste stream, and pigments are very expensive. So the question was, could we separate the pigments back out and reuse them? Okay. And the answer is, well, and the question was then, can we use hydrocycling to do that? Because hydrocycling to work requires large volumes of material. So when you're doing glazing in a production line, you're generating a lot of overspray. Okay, and then what you do with that overspray is that you wash it off the walls, so you end up with a more dilute suspension. Then what they typically do is put it in a big vat and let it settle, decant off the clear water on the top, concentrate the material on the bottom, but it's very difficult to separate. Well, in hydrocycling and in other processes, you don't want a high concentration of particles. And the reason is this, is that if I have a large particle and I have a small particle, the sedimentation velocity of the large particle is faster than the small particle. It will capture this particle, right, and you end up with that. So it's called inertial capture. So if I have a high concentration of particles, my particles do not settle independently. So you need them to settle independently. You need the same thing in hydrocycling. You like the particles to act independently, then you can separate them. So this whole thing about glazed waste and waste in an industrial process, we could potentially use it for beneficiating other waste streams, provided that my particle size and my densities are not offsetting, if you will. And that's what this plot is showing us. So the x-axis is density. We go from about 2.6 up to about a little over 5.5. And then I have particle size on the y-axis on a log scale. And that's really important for us that it's on a log scale. And so here's 1 micron, there's 10 microns, etc. And then these different bands that you see here, the dot in the middle represents the mean of the particle size distribution, and the width of the band indicates the 90 and the 10% limit. So it's basically 80% of the particle size distribution is represented by the bands. Good? And then, because we're clever, we color-coded them based on the pigment color. Good? What do you see? There are a series of lines written here, drawn on here, and these are the sedimentation velocities corrected for density and size. Does that make sense? Okay, so if I was at a density of 3 grams per cubic centimeter, and I have a particle size that's roughly, say, let's see, that's 1, 2, 3, 4, 4. There's my sedimentation velocity, would be 5 centimeters per hour. If I was at 5 grams per cubic centimeter and somewhere around 0.3 microns, they have the same sedimentation velocity. Well, that doesn't seem like a big difference. But what you see is that these particle size distributions that are drawn here overlap a broad range of sedimentation velocities. right? That means that the coarse particles that are blue, which are represented by the top, overlap the finer particles of the red or whatever color that is over here, or the yellow at the end, and now I have a problem. If I put them in a hydrocyclone, I can't separate those particles because they are all moving at the same velocity based on the difference in size and density. Good? So that's the idea behind hydrocycloning. If the density of powders are similar, then you can get good separation. Or if the density of, say, the larger particles and the smaller particles and their sizes are sufficiently different. So what you're really looking at in this equation is mass, right? So size times density, or yeah, so diameter times density, and you're going to have to, you correct for volume, but you just assume spherical, so you can do that calculation easily. You get a mass of the particle. A mass of, say, 0.01 grams made out of one material with high density, if it matches the mass of 0.01 grams of another material with a lower density, anything that's 0.1 grams in terms of 0.01 grams settles at the same velocity. Therefore, I can't separate things out. Good? Okay. So, beneficiation processes, as simple as particle sizing, can be quite complex, or froth flotation. And then we get into the situation with the Baer process. Okay, the Baer process is immensely important industrially. So, the Baer process was invented by a guy named Baer. Same people, by the way, who made aspirin eventually and that kind of thing. Huge company located in Germany. Originated in Germany. Okay, still around. Broken up after World War II, got back together eventually. Okay, Baer process still exists, and the Baer company still exists. But now it's a process used all over the world, and we use it to beneficiate bauxite. Bauxite is an ore, it's usually aluminum hydroxide plus iron oxide, and sometimes iron hydroxide, or FeOH3, OH2, some other impurities. But these materials in bauxite, the aluminum oxide, aluminum hydroxide, and the iron are intimately mixed together. So they're on a very fine-grained scale. You can't separate the aluminum hydroxide from the iron oxide by froth flotation. You can't separate it by milling. You can't do dense medium separation because you can't separate the particles. Okay, so you have no other alternative but to go through what's called the Baer process. And what you do is that you dissolve out the aluminum hydroxide, and the iron oxide and hydroxide is not susceptible to that dissolution. So you will literally dissolve the aluminum out, okay, and you form then what's called a liquor, all right? And then you can adjust the pH and precipitate back out that aluminum hydroxide after separating the iron from it, okay? What do you know about this process? What would you guess about this process?
Very expensive.
It's extremely expensive, okay? It is probably pretty much the most expensive industrial process for metals beneficiation or beneficiation for making metals. We did this talk over the summer. It's actually worthwhile to bring this up at the moment. Having to do with the not economic, but energy costs associated with manufacturing. And it had to do with architectural terracotta, because that was the conference. And the results were actually quite surprising, to me anyway. Let's see. That looks like it. Perfect. And here is the energy cost to produce materials. And I was surprised at this because aluminum metal is the most energy intensive process of any of the materials that we look at. Copper and stainless steel are fully half the cost, energy costs associated, or energy costs necessary to make aluminum. Plastics are surprisingly energy intensive to produce. Why? Great question.
Just kind of guessing, but because you have to take like polymers and have them actually like bind to each other.
What do you start with? Oil, petroleum, or some other material, right? You have to first have to beneficiate that material. Oh, just because it's tar oil coming out of the ground doesn't mean it's ready to go, right? I mentioned the sulfur out of the oil sands, right? You're going to have to beneficiate that material. Shell had a huge production in the North Sea because the crude coming out of the North Sea and the ocean floor was very low molecular weight, which is really rare. You know, as the molecular weights get higher, you have to spend more energy and more time in order to separate them and crack them into smaller pieces. Then you got to form them back together. So you have all these process steps. It's very energy intensive. Steel by itself is cheaper than stainless steel. Glass is a quarter or an eighth of what it costs to make copper or stainless steel. Plasterboard is more expensive than you might think because you mine gypsum, by using steam, which is expensive, a lot of energy there, to drive off the waters of hydration in the plaster of Paris. Then you rehydrate it, cast it into a big sheet, and then you have to dry it. So it's a remarkably expensive, in this perspective, material to make. And you don't think of that, but evaporation of water costs a lot of money. It's very, very energy intensive. We will talk about that as the semester progresses. Cement is relatively cheap. By comparison, everything else on the list, except for clay. Okay? So even though you have to fire clays, you have to dry them, you have to mine them and beneficiate them, it still turns out to be one of the least expensive energy costs in order to manufacture. So, here we are. All right, so let's talk about bauxite processing. Okay, so bauxite is mined. Where do you find bauxite in the world?
Australia.
Australia. Good. Where else?
South America.
I don't know. Maybe. Where are the big bauxite mines now?
There's some in Germany.
Hungary. Reason that Germany invaded Hungary in World War II was because of the bauxite mines and aluminum production. A lot of history here, right? So, does anybody know Jim Jones? Do you ever hear the expression "drink the Kool-Aid"?
Mm-hmm.
What does that mean? Did you work for Corning? Just kidding. Jonestown. This is all way ahead of your time. Mass suicide in Jonestown. I don't know how many. Bunch of people, hundreds of people. Right. In Guyana, which is or French Guyana, which is on the northern tip of South America. Right. Drink the Kool-Aid. Famous before that for bauxite mines. Jamaica is the other big one. Huge bauxite mines in Jamaica. Used to be bauxite mines in Arkansas. Those are now mined out. There's still aluminum processing plants in Arkansas. There are bauxite processing plants in Arkansas at the location where the mines used to be. Bauxite is imported from not so much from China, some from China, but a lot from Australia, and then Jamaica and the northern edge of South America. There's only a few big bauxite producing areas. Hungary is not a big bauxite producer anymore. They were in World War II. In around World War II, 1940s, they discovered bauxite in Jamaica. I have an old mineral book from the 40s that talks about the potential of bauxite mines in Jamaica that is now one of the most productive bauxite mines in the world. Okay, so you mine the bauxite. Okay, it gets stored. It goes into a conveyor. And then here it gets milled to give us a size that will react reasonably. It comes in. It gets heated with steam. Sodium hydroxide is introduced to the ball mill. So you end up with sodium hydroxide in contact with bauxite. And then it comes into a process and steam is injected to heat the system, because as you drive the temperature up, the aluminum dissolution rate goes up dramatically. Okay? So by warming the system, you can dissolve the aluminum hydroxide out much more rapidly. That comes into, that's called a digestion vessel, so that's where the material is actually dissolved. Then into a flash tank or blow-off tank, And then this material, the red mud or the slurry that contains iron, is now called red mud. So if you have seen references to red mud, okay, there was a famous, somewhat famous, I suppose, event several years ago, less than 10, I believe, where the red mud basically is the byproduct of producing aluminum from bauxite. No one has really found a use for it yet. It's not big enough to justify looking at it as an iron ore source to make iron. There's just not enough of it, even though there's millions of tons of it. It's not enough to justify that compared to iron ore that's being mined. And so the consequence is that this material sits around. Okay. Now, they drive the pH up to somewhere around 14. The red mud then that comes out, okay, that slurry is around a pH of 14. And it sits in these big lakes, basically, for long periods of time. In Hungary, by the Danube River, one of those dikes broke, and I think it was about 10 years ago. And then red mud flooded this town. Not a pleasant situation. That material comes through, goes through clarifiers to the red mud lake. Okay, so you're removing excess liquid. pH can be very, very high. And because you've used that high pH in order to dissolve the alumina, what comes out, they can filter press some of it, but that's not actually true. This filter press is filter pressing to consolidate or concentrate the aluminum to remove excess water. All right, and then that comes into this liquid here. As actually, it's called a pregnant liquor. That means it's high temperature and it's saturated with aluminum. And what they do then is they will precipitate aluminum hydroxide by driving the pH down. So they take that pregnant liquor and they drive the pH down by the addition of sulfuric acid. Okay? And what that does then is it precipitates aluminum hydroxide. Okay? That precipitation of aluminum hydroxide, apologies, the filter press actually is to collect the last iron particles, the fine iron particles out of that suspension, and then the solution of aluminum goes through the filter press and goes to the precipitation reactor. And that material then, by driving the pH down, precipitates aluminum hydroxide. So you start with aluminum hydroxide and you precipitate aluminum hydroxide at the end. But you also get out of that, because you have you add sulfuric acid. Okay, and what you have is you have sodium plus this aluminum in solution and plus sulfuric acid. You end up with then aluminum hydroxide again plus sodium sulfate. Okay, so sodium sulfate soluble in water, that's good. Particles precipitate out. Okay, that precipitation process, you pull those off. But the problem with this is that you end up then with a sodium impurity typically within your aluminum hydroxide. Okay, if you take your aluminum hydroxide and you heat it, you form aluminum oxide plus water. If you do our math, we do a 2 here, and you end up with 2 waters here. Okay? So with heating, you form aluminum oxide. This temperature is typically around 600 degrees C to 1,000 degrees C. And by the time you get to 1,000 degrees C, you have alpha alumina, which is what we most commonly know, okay, as alumina. If you're at lower temperatures than that, there's a whole series of different aluminas you can form. Gamma alumina, delta alumina, etc. Okay? So you form aluminum oxide. The largest use of aluminum oxide is to then go to what's called a Hall-Perot cell, and you precipitate out aluminum metal. You actually do a reduction, electrolysis reduction, to extract the aluminum or remove the oxygens to end up with aluminum metal. Okay, so that's where most of it goes. And that means that at the place we start, this bauxite, there are several grades, and one is metallurgical grade. Okay? There's a refractory grade, there's an abrasive grade, there's a chemical grade, and there's a metallurgical grade. Most of the bauxite that's processed is metallurgical grade. Okay? So, after precipitation, it goes through a kiln, it gets calcined, and then it goes off to be shipped. So that calcination process dries off the waters and forms aluminum oxide. A friend of mine figured out that the issue is that when you heat treat this material, right, the sodium, because your temperatures are high, if you're above about 900 degrees C, the sodium goes into the vapor phase. Good? Okay. So when that material comes out of the calciner, if you vent that gas off of the top, the sodium goes with it. If you don't vent the gas and the material just cools, the sodium recondenses back on the surface of the alumina. Okay. Then you have to wash the alumina to remove the sodium, so you have an extra process step. He invented a process by which you vent that high temperature gas, and with it goes the sodium, and you can produce extremely low sodium aluminum oxide through the bare process. If you vent that gas, and that would happen actually right here, okay? So this is all heated, and you have gas above the aluminum oxide. If you cool that system down, that gas condenses back, and that's typically sodium, and then you end up with sodium on your aluminum, okay? Pictures of it to give you an idea of temperature. These are the minerals that show up in bauxite, okay? Gibbsite is what you're looking for. Bayamite and diaspore are both forms of aluminum hydrate, hydrate alumina. As you go from bayamite to diaspore, your temperatures and your pressures necessary to form this reaction go up. That means your costs go up. Goethite, hematite, those are irons. Magnetites to the right, those are iron compounds. Ilmenites and iron, titanium. You have antitate, rutile, and brookite, they're all titanium. Then you have polysite and kaolinite and quartz. We don't care about quartz because we can separate quartz out pretty easily. It's also not reactive or not very reactive in the system. We care about clays though. Polysite and kaolinite, if that's in the system, there's too much clay, you can't process the bauxite because in that digestion step you will dissolve that clay in, and then you end up with silicon, and then you end up with silicon in your aluminum and you can't deal with that. We prefer gibbsite, 135 to 150 degrees C, so you know it's under pressure. Plus it's a high concentration solution, drives up to the boiling point. Okay, there's your reaction. Bayamite, you have to go above 200 degrees C, that becomes expensive. And diaspore, you have to add pressure to it. This is your reactive silica that I talked about, reactive silica, excuse me. If the reactive silica is greater than 7%, the process is not economical. That fits into the grades of the bauxite. So if they're grading the bauxite and they come back and they go, there's too much clay, then it can't be a metallurgical grade, and they have specifications for those grades. Okay. Monday, we are here 10 minutes to 1. Good? And we will hop on the bus, okay, and we will go down to the gravel pit. We should be back in plenty of time for you to make it to your class. Good? Okay. If you have your own hard hat, please bring it, just in case.